Welcome to chapter 13. This chapter is on the chi-square test. It is pronounced chi, although lots of people like to pronounce it chi or chai, like the T. But it is actually chi-square. Okay, here we go. So the chi-square test is symbolized, you can see it there on the screen, by that kind of italicized X and that number 2 superscript, or that squared symbol. And the chi-square test is a non-parametric test of significance, which means that it makes no assumptions about the shape of the distribution. It doesn't assume that if you were to plot your data, it would take a mesocritic shape or a normal curve. It doesn't assume that it would take the shape of a skewed distribution and be positively or negatively skewed. It just makes no assumptions about the way your data would look if you were to plot it. So another important thing to note is that when we use a test that doesn't make assumptions about the distribution, it is called a non-parametric test, and it is also called a distribution-free test of significance. So when to use the chi-square, you should use a chi-square test if you have nominal data. So if you have categorical data or words in your data set, the way you're collecting data is using names, words, categories, then you're going to have nominal data and you would need to use a chi-square. A chi-square test tests the hypothesis of difference. And there are two chi-square tests that you're going to be learning in this lecture, a one variable and a two variable. So in addition to when you're reading a research design on your homework or on the quiz, in addition to looking for nominal data and a hypothesis of difference to determine a chi-square test, you would also need to pay attention to how many variables there are, how many independent variables there are, so that you can determine if you're going to do a one variable or a two variable. So we'll talk about that in a minute, but before we get off this slide, a couple more things to say about parametric versus non-parametric tests. So parametric tests like the ANOVA are usually preferred because they have greater sensitivity. However, when the assumption of normality is violated, meaning that you're not expecting the curve to take a mesocritic shape, then a non-parametric test like the chi-square can be just as powerful. And there's other non-parametric tests listed there on the slide. So if you had nominal data, you could do a binomial test. And then if you had ordinal data, you could do the sign test or the Wilcoxon test or the Mann-Whitney test. So just depending on the type of data you have and the shape of your distribution, there are a lot of different tests that are available to us as statisticians. Okay, so the first chi-square we're going to learn is the one variable chi-square. And it is called a one variable chi-square because you use it when you only have one independent variable, but that one independent variable has a number of levels. This one variable chi-square test is also called the goodness of fit test, or a 1 by k, k representing the number of levels you have. So a 1 by k chi-square. So if you look at the example here underneath the formula, we'll come back to that in a moment. In orange, it says a researcher wants to know if there is a significant difference in people's preference for fast food restaurants. And so the IV is fast food restaurants, and there's 3 levels of that. So K is 3 with In-N-Out, Bakers, and McDonald's. And then the DV is going to be the number of people preferring each restaurant. And so we have some new symbols here that we haven't seen before, like the FO is equal to the actual number of preferences, so what people said they preferred. And then the FE is the expected number of preferences that are based purely on chance. So for example, the FE is calculated by taking your N, your number of people, divided by your number of levels. So if we had 75 people, we would expect the FE to be 25, because just by chance we would assume that if we had 3 levels and we had 75 people, we would just divide up those 75 people into an equal number of people preferring each group, and that would be our FE. And we do that by taking N of 75 divided by K of 3 would be 25. So at any rate, we're expecting there to be 25 people in each group or preferring each type of fast food restaurant. And so this goodness of fit test, as it is called, is to see if the data we get fits with what we expect. However, of course, we hope to find that it doesn't fit, that the frequencies observed are significantly different than the FE frequency expected, and then we would be able to reject HO. So that's why it's called a goodness of fit. And to be more specific, it would be called a 1/3 goodness of fit test or a 1/3 chi-square test for this specific example. And the reason being that we have one IV, which is fast food restaurants. So 1, and then the by 3 is that there are 3 levels of that fast food restaurant. So a 1/k, or in this case, to be specific, it's a 1/3. And so if you look at the formula, you can see that there's the sigma sign there, and the numerator is the FO minus the FE, so what we would expect by chance minus what we actually got. Then you're going to square that value to get rid of any negative variance, basically, and then divide by the FE again. And after you do that, for each level, you're going to add up the values that you got, and that's going to equal your chi-square. But of course, I will be showing you that in just a moment on the worksheet. So after you calculate through that chi-square formula, you're going to end up with your test statistic, your chi-square value. And so you're going to need to evaluate that chi-square. And in evaluating it, you will be determining if you're able to reject HO. And HO, in this case, is the null hypothesis, of course. So in this case, it is FO, which is frequency observed, is going to be equal to FE, frequency expected. Of course, we hope to reject HO and find that HA is actually correct, or the alternate hypothesis, which is that our frequencies observed do not equal our frequencies expected. So in order to make that evaluation, you're going to have to get crit values from table I. Table I uses degrees of freedom, and the degrees of freedom calculation for a 1-variable chi-square are k minus 1. So on table I, using your degrees of freedom, you're going to get crit values, and if your calculated chi-square is equal to or greater than the table value, you'll get to reject HO at the appropriate level. Okay, so let's check out the chi-square worksheet and learn how to do a 1-variable chi-square test. Okay, so this is the chi-square worksheet, and the top portion of the worksheet is a 1-variable chi-square, also known as the goodness of fit test. And then the bottom half of the chi-square worksheet is the 2-variable chi-square, also known as the test of independence. So we're going to start up here with the 1-variable chi-square, but in both cases, the formula for the chi-square is the same. So you need the chi-square symbol, and then a big sigma. That's a weird sigma. And then the numerator in parentheses is the frequency observed minus the frequency expected. You're going to square that, and that's going to be over the frequency expected. So we need to kind of just get a lay of the land here, pull out some of our puzzle pieces. The first thing we want to know is how many people are in the study. So it looks like this particular study for the 1-variable is focused on eating preferences of 135 people that were given a survey. So that lets me know that the N is 135. And I can also see right here this value of 135 off to the side, and that is my N. So N equals 135, and then I also need K for my degrees of freedom and other calculations. So K is the number of preferences, so there are 3 choices of fast food restaurants, so K is 3. So now we're going to start moving through our formula. So it looks like we need the FO and the FE. So the FO is the frequency observed, and those are the values given, and they'll always be given. So here they are: 62 people preferred In-N-Out, 40 preferred Bakers, and 33 preferred McDonald's. If you add these all up, they would give you an N of 135. If on a quiz or a homework you were not given the n, but you still would need it for your formulas, so you'd have to calculate it on your own. And the way you would do that is by adding together all of your FOs, and that would give you your n. Because each person that's surveyed is only able to give one response, so you can't say you prefer both In-N-Out and Baker's, for example. So since this is one response representing one person, you can add them up and you can get the total number of people in your study. Okay, so the FE calculation for a one variable, the formula for that is N divided by K. And so for a one variable, that's really easy. It's going to be the same for all levels of your fast food restaurant independent variable. So you're going to take the N of 135 and divide that by 3. And that is going to give you an FE of 45. So you're going to do that for each restaurant choice. And so you're going to have 45 as the FE for all of these levels of fast food restaurants. Okay, so 45 is the FE for each of the levels. And then the next step is going to be to subtract the FE from the FO, and we're going to do that for each level of the IV. So if I were to take the FO of 62 and subtract it from the FE for the In-N-Out column here, put that in parentheses, square that, and divide that by the FE again, so 45. Okay, and I'm going to go ahead and put the addition symbol there because I'm going to be summing up all of my calculations for each level of the IV. So then I'm going to take, for Baker's, the FO of 40 minus that FE of 45. Put that in parentheses, throw the squared symbol after that, and then I'm going to divide by the FE like my formula says. Okay, and then I'm going to add that to the formula for McDonald's. So here I have an FO of 33 minus the FE of 45. I'm going to square that and divide it by the FE of 45. Okay, so 62 minus 45 is 17. And I'm going to pull down that squared symbol, divided by 45. And 40 minus 45 is negative 5. Again, pulling down that squared symbol. Oh, and my plus signs between the formulas. And then 33 minus 45 for McDonald's, numerator there would be negative 12. And I'm going to pull down that squared symbol and divide by 45. Okay, so the next step is going to be to square all of the values so on the numerator. So 17 squared is 289. So 289 divided by 45 plus negative 5 squared for the Baker's column. I'm going to change that to a 25. Negative 5 squared is 25 divided by 45. Just pulling down that denominator. And then negative 12 squared is 144. Again, pulling down that denominator of 45. And then I am going to do the division here for each of these. So 289 divided by 45 is 6.42. And 25 divided by 45 is 0.56. I'm going to add that to that 6.42 in a second. Let me put my plus symbol here. And then 144 divided by 45 is 3.2. Okay, so then if I add all those values together, I would get 10.18. And that is going to be my chi-square. So I'm going to put that on the answer line as well. Okay, so once you have your one variable chi-square, the next thing you'll have to do is evaluate your test statistic to see if you've reached significance or not. And so to do that on a one variable chi-square, you're going to use table I. And you'll need to calculate degrees of freedom, and the degrees of freedom calculation for one variable chi-square is just k minus 1. So in this case, k is 3, so 3 minus 1 equals 2. So I'm going to put the 2 in my parentheses there. And then I'm going to grab my table I. And using 2 degrees of freedom, I could see that the crit value at the 0.05 level is 5.99. So I'm going to write that here next to the 0.05. And then the 0.01 using 2 degrees of freedom is 9.21. So I'm going to write 9.21 on the line there next to the 0.01. And then I will draw my curve. And so I have my 0.01 at 9.21, my 0.05, 5.99. Let me shade those a little. Okay, so our chi-square was 10.18. I'd say that would be over here in our 0.01 region. So we're going to reject HO. P less than 0.01. And then I'm going to write a sentence regarding what this value of 10.18 means, or what does it tell us. And so what it tells us is that there is a significant difference in restaurant preference. So if I were to write out what this means, I'm going to do it on the side here. There is a significant, difference in restaurant preference. Okay, and so then I'm going to describe the difference, and to do that I'm going to refer back to the FOs, and I'm going to see which restaurant was preferred the most, the least, and then in between. So it looks like In-N-Out was preferred the most, followed by Baker's, followed by McDonald's. So I would write that here. In-N-Out was, I'm going to just make that a period, not a comma. Okay. In-N-Out was most preferred, followed by McDonald's, and then followed by Baker's, and then McDonald's. Baker's, and then, McD's. Okay, so there is a significant difference in restaurant preference. In-N-Out was most preferred, followed by Baker's, and then McDonald's. And again, I know that second sentence because I referenced my frequency observed and saw In-N-Out had the highest number, then Baker's, then McDonald's. So now we're going to look at the two variable chi-square test, and it's called a two variable chi-square because you use it when you have two independent variables. This is also called the chi-square test of independence, or an R by K chi-square. Again, K is the number of levels of the IV. And as you see here where it says calculation step 1, the first thing you're going to do is make a contingency table, which looks very similar to the block of cells we made with the factorial ANOVA. And so when you are looking at that purple font that says it's an R by K chi-square, two variables also called an R by K chi-square, it's referring to the rows of the contingency table that you're going to make, or the block of cells that you're going to make, and then K is the number of levels. But I always like to think of it as an R by C chi-square, because it's really looking at the number of rows by the number of columns. But I'll be showing more on that later when we get to degrees of freedom calculations. But technically, this test can be referred to as a two-variable chi-square, an R by K chi-square, or a test of independence. Okay, so for the calculation, first you have to make a contingency table, which is a block of cells. And same as factorial ANOVA, you label each column with a level of the first IV, and then you label each row with a level of the second IV. You put the corresponding frequency observed in the cell, and you add the cells in the same rows together to get what's called the frequency row, and then you add the cells in the same columns together to get what's called the frequency column, and you put those outside of your contingency table at their appropriate locations. Again, going to show you that on the worksheet coming up. After you do that, you'll be able to plug your FR and your FC into your FE formula. So you multiply your FR and FC divided by your overall N. You do that actually for each one of the cells in your contingency table. And then you have your FE. By doing that calculation, and FO is always given to you. It's the frequencies observed, so the data basically. And so you take the FO and the FE and you plug them into that chi-square formula. It's the same as it was for a one variable chi-square. So the only difference here between a one variable and a two variable is the calculation of the FE, and then just the concept of the contingency table and drawing it out. But once you have the FO and the FE, it's the same formula as the one variable chi-square. So you calculate through that. And then you're going to get your chi-square test statistic, or your value, and you're going to have to compare that to the crit values that you get on table I. On table I, when you're doing a two-variable chi-square, the degrees of freedom calculation are a little bit different than a one-variable chi-square. In a two-variable chi-square, you calculate your degrees of freedom by multiplying the number of rows you have minus 1 by the number of columns you have minus 1. So here on the slide, you see in the green font under step 3 that it says the degrees of freedom calculation is rows minus 1 times K minus 1. I always just mentally substitute that K with a C. It just makes more sense to me. So number of rows minus 1 times the number of columns minus 1 will get you your degrees of freedom. And then you look up those degrees of freedom on table I to get your crit values. And go back, grab your chi-square test statistic and see if it's equal to or greater than those crit values. And if it is, you get to reject HO. Okay, so let's take a look at the worksheet again so we can learn how to do a two-variable chi-square. Okay, so now we're going to move down here to the two-variable chi-square, or the test of independence. And this one has 3 levels of the first IV, which again is restaurant preference, or fast food restaurants. And then the second IV is gender. And so there's 2 levels of gender. So 3 levels of fast food restaurants and 2 levels of gender. So we would say this is a 3 by 2 chi-square. And so when we have a two-variable chi-square, we are still using our chi-square formula. The only difference is in the calculation of that FE. So the way that the FE is calculated on a two-variable chi-square is using this formula here. FE equals the frequency row times the frequency column over N. So since we need the N, and that's usually pretty easy to identify, we'll start there. So it says eating preferences of 50 people were surveyed. So I know my N is equal to 50. And then also over here is my N. And so I'll notice that these values here on the outside of, this is a contingency table. And so each cell here is telling me how many people preferred the restaurant and their gender. So the cell outside or the number outside of the cells in this case is the number of men, the number of women, and then the columns here, the the values that you get from the columns here are all the people that preferred McDonald's, all the people that preferred Baker's, and all the people that preferred In-N-Out. So if you add up all the values for a restaurant preference, you'll get, fast food restaurant, you'll get 50. And if you add up the people for each gender, you would get 50. So the N is 50. And then the values inside the cells on the top, those are the FOs. So sometimes it's helpful when you're learning Chi-Square to just label the FOs so you know. And then all the values here, these two values outside of the rows, these are called the FRs, your frequency row. And then the values down here, the bottom of the columns, these are called your FCs, or your frequency column. Okay, so you have all your FOs. In order to do the formula, you need your FEs. And so your FE calculation, you're going to do over and over and over again. You're going to do once for each cell. So in this case, we're going to do it 6 times. And I like to color coordinate. So I will be highlighting the cells and then their corresponding formulas. So I'm going to start calculating the FE for men In-N-Out. So this cell here that I've just highlighted. So to calculate the FE for the In-N-Out men, I am going to take the FR for this highlighted cell. So I'm just going to pull my pencil across and see that the FR is 25 for that cell, or for that row. And then the FC for that same cell is the columns. And so the FC for that cell is 18. So I'm going to put 18 here. And then I'm going to divide that by the N of 50. Okay, so I'm just going to put that in a square that matches the cell, so you know which formula represents what. Okay, and so if I calculate through this formula, I should get I should have left that in the cell here. I'll fix it. A 9. Not bad. Okay, and so that 9 is the FE for men In-N-Out. So we'll put the 9 there. Okay, and now we're going to do the frequency expected, or the FE for Baker's men. So I'm going to highlight that cell in green. Oops, green doesn't work very well. In green. Okay, so Baker's men. So for Baker's men, I'm going to take the frequency row, which again is 25. And I'm going to multiply that by the frequency column for this green cell, which is 19. And that's going to be divided by the N of 50. And that is going to give us an FE of 9.5 for the Baker's men. So I'm going to square that off in green so you know it goes with Baker's men. And I'm going to put the FE in the little triangle on the bottom of that cell. Okay, now I'm going to do the FO for McDonald's men in pink. Okay. So I'm going to take, for the pink cell, the FR, which is 25, plus the FC for the pink cell, which is 13. And I'm going to divide that by the N of 50. And that is going to give me an FE of 6.5. Oops, why did I do an addition sign? 25 times 13 divided by 50 is going to give me 6.5. So I'm going to put 6.5 down here and block off that formula in pink so you know it goes with the McDonald's men. Okay, so 25 times 13 divided by 50, 6.5. Put it there. Now, in and out women. We will do them in purple. Okay, so our in and out women, we're going to take the FR for them, which is 25, and multiply it by the FC for them, which is 18. Divide that by 50, and we get 9. So this is just a coincidence. Your FRs are normally not the exact same value. So generally we don't end up getting the same numbers for the same columns of cells, but in this case we are, since those are the same. So we got a 9 there, and we're gonna block that off in purple so that we know it goes with the in and out women cell. Okay, now we're going to do the baker's women. I'm gonna block them off in yellow. Ooh, that's real hard to see. Okay, well, we'll make it work. All right, so we're gonna take the FR for baker's women, which is 25, and we're gonna multiply that by the FC for baker's women, which is 19. And divide that by an N of 50, and that's going to give us 9.5. Put that in that lower triangle. 9.5 is the FE for baker's women. Okay, now we're going to do, what colors do I have with red? We're going to do McDonald's women. Okay, so for the McDonald's women, the FR is 25, and the FC for the red cell here is 13. And so that's going to be divided by 50, and that will give us 6.5. So I'm going to place that there, 6.5, and let me go ahead and block it off in red. So you know it goes with McDonald's women. Okay, and then what we are going to do is complete our formula. Obviously, we have to do this part in the square here. We have to do that one time for each cell, and then we add them all up. So I'm going to start by taking the calculation for the in and out men, the FO minus the FE squared divided by the FE. So the FO for in and out men is 10 minus the FE of 9. And that is going to be squared and divided by the FE of 9. Okay, and I am going to block that off. Is this the right color? Yeah, in this color, so we know. Okay, and then we're going to do the green. So that's baker's men. So I'm going to take the FO of 8 minus 9.50. Don't forget the squared symbol. Divided by the FE of 9.50. And let me go ahead and square that off in green, so you know. Okay, and then we're going to do the McDonald's men, which is going to be 7 minus 6.5 squared over 6.5, and that is pink. So I'm going to put that in pink so you know. Okay, now we're on the second row here for the women. We're going to take the FO of 8, in and out women, 8 minus that FE of 9. Don't forget the squared symbol over an FE of 9. And we'll go ahead and block that off in purple. Okay. And then we have baker's women, and their FO was 11 minus their FE of 9.5 over that FE of 9.5, and they were yellow. Let's go ahead and do that in the yellow. I can't really see. Let me see if I have another. A little better. Yellow. Okay. Last one is this red cell here, McDonald's women. We're going to do the FO of 6 minus the FE of 6.5 squared over the FE of 6.5. And let's go ahead and mark that off in red. Okay, so I'm just gonna calculate through each of these squares down here. So if I calculate through 10 minus 9 squared over 9, I get 0.11. I'm going to add that to what I get for the green. So if I take 8 minus 9.5 squared divided by 9.5, I get 0.24. And I'm going to add that to what I get for the pink cell, which was McDonald's men. So if I take 7 minus 6.5 squared over 6.5, that's going to give me 0.04. I'm going to add that to what I get from the purple square. So if I do 8 minus 9 squared over 9, I'm going to get 0.11. And if I do 11 minus 9.5 squared over 9.5, I am going to get 0.24. I'm going to add that to the red cell. So 6 minus 6.5 squared over 6.5 is going to give me 0.04. Okay, so then if I add 0.11 plus 0.24 plus 0.04 plus 0.11 plus 0.24 plus 0.04, I am going to get my chi-square value of 0.78. Okay, so I'm going to put 0.78 up here on my chi-square line. And now I need to evaluate it for significance. And to do that, I'm going to use table I. But on a two-variable chi-square, for table I, the degrees of freedom calculation is a little different. So I'm just going to put table I here so you have it. But the way you calculate it is the number of rows you have minus 1 multiplied by k minus 1. But I like to, just for my own reference, cross out the k and put a c. It just makes more sense to me that way, but that's not the technical way to write the formula. But that is the way that I calculate it. The number of rows I have minus 1 times the number of columns I have minus 1. So if I were to take the number of rows I have minus 1, I would have 1, 2 rows, so 2 minus 1 is 1. And if I were to take the number of columns I have minus 1, so I have 1, 2, 3 columns, so 3 minus 1 is 2. So 1 minus 2 is 2. So I'm going to put that in my parentheses here. And then on table I, using 2 degrees of freedom, my crit value is 5.99 at the 0.05 and 9.21 at the 0.01. So I'm going to put those values on the crit values line, 5.99 and 9.21. And then I can see that my chi-square is 0.78, which is not even close to the 0.05, so it's certainly not going to be bigger than the 0.01. So sadly, I'm going to have to accept HO. So what I would say here is that there is no significant difference in restaurant preference between men and women. However, if there was a significant difference, I would explain the cell that looked the most different from the other cells, similar to how I did with a factorial ANOVA. So let's say that this in and out men, the FO was like 100, okay? Then I would describe this one cell when I'm writing the sentence for this chi-square problem. So if this was significant, I would look to the cell that has the FO that's the most different. Here we're pretending this 10 is actually 100. And I would describe that cell. So I would write, if the FO said 100, it does not. There's not a significant difference. But if it did, I would write, there is a significant difference in restaurant preference between gender, with men preferring In-N-Out significantly, you know what I mean, significantly more than women. Okay, and that is the Chi-Square worksheet. So I'm going to give you just a little bit more info on the Chi-Square test. If you are looking at the Chi-Square formula and you calculate through it, a good rule of thumb is that your calculation for the FO minus FE, if that number is small, then your Chi-Square test statistic, the final value that you get, should also be small. So a little bit of a way to check your work there. If the FO minus FE is large, then your Chi-Square calculated value should also be large. Another thing to note, and this is important for quizzes, is each observation must be independent of all other observations. In other words, you cannot make several observations of the same person and then treat those observations like they came from different people. So a person cannot be marked as a Republican and a Democrat. A person can't say that they prefer In-N-Out and McDonald's. They have to choose one. So that makes it an independent test. A chi-square will never produce a negative value because you can't have a negative number of observations. So if you calculate your chi-square and you get a negative number, then you know that you need to go back and check your work because something went wrong. And that concludes Chapter 13. Thank you for listening. We'll talk to you on the next one. Have a great day.